Today we're going to talk about kernelization, which is an idea that we've already seen. And the idea in kernelization was that we want to take an instance of a parameterized algorithm and we want to just make it smaller and smaller. And at some point, we want to get to an instance that is so small we can just do some sort of maybe exponential time algorithm on it. Maybe we can just try everything and we can just solve it by brute force. So one notion that we have already used, but I haven't really defined, was this notion of a reduction rule. So let's say I have some parameterized problem, and let's say that my parameterized problem is L, which is a subset of, well, sigma star times n, right? Because I have some input and I also have some parameter. Now, what is a reduction rule? A reduction rule is basically a rule that gets some input. So let's say it takes input xk and turns it into another input. Let's call that x prime, k prime. But it doesn't change the answer to the problem. So another way of looking at it is that let's say that this reduction rule is some function f. It takes xk, gives me another input x prime, k prime. And then xk should be a yes instance. It should be in L if and only if x prime, k prime is also a yes instance. So when I talk about a reduction rule, or when I say a rule is sound or safe, this is what I mean. I mean, it doesn't change the answer to the problem. If it's a no instance, it remains a no instance. If it's a yes instance, it remains a yes instance. Now, remember that we wanted to find FPT algorithms, or fixed parameter tractable algorithms. And we said that in these algorithms, the runtime has to be polynomial in the lengths of the input, but can depend arbitrarily on the parameter k. But the dependence on k had to be multiplicative. It couldn't be in the polynomial's degree. So when I'm talking about an FPT algorithm, I basically mean an algorithm that has a runtime of n to some constant, and n is the length of x, times some function of k. And yeah, this function has to be computable, but we don't need anything more than that. So, and then we said that a problem is FPT if it has an FPT algorithm. Okay. Now, we want to use ideas that are similar to these reduction rules to start with a large instance and just make our instance smaller and smaller until the size of the instance becomes bounded by a function of the parameter. And when that happens, I can say I can just use brute force and it doesn't matter. The rest of my runtime is only going to depend on my parameter anyway. Okay, so let's give an exact definition of this. So what is kernelization? And sometimes this is just called a kernel instead of kernelization. So a kernel for a language L is just an algorithm. And what does this algorithm do? It takes instances of this language, it takes instances of our problem and turns them into other instances. So that takes, let's say, xk as input and outputs x prime, k prime. Now, what conditions should be satisfied? Well, first of all, I don't want my kernel to change the answer. So I want to know that, first of all, xk was a yes instance, was in my language, if and only if x prime, k prime is a yes instance. Now, what else do I want? Of course, I want this algorithm to run in polynomial time, right? Because if just my reductions and making the instance smaller takes more than polynomial time, then I can't really have an FPT algorithm at the end of it. So I want to say that A runs in polynomial time with respect to the length of x, which is also shown by n. Okay. Now, what else do I want? Well, I want my final instance to be small, right? And by that, I mean that I want my final instance to be bounded by some function of my parameter. So maybe I can say such that there exists some function, let's call it g, also from n to n, and you can say that it should also be computable. And what do I want? I want the length of my output, the length of my small instance, to be bounded by this function, by g of k. Okay? But even this is not completely enough, because you see, by this definition, I'm taking some initial instance and I'm just making it smaller in polynomial time. And at the end, the size of the instance is bounded by some function of my parameter. But this is not saying anything about the parameter in the smaller instance. So if you are very paranoid, it might be that we come up with an algorithm that actually makes the input smaller, but explodes the parameter, makes the parameter really large. So I don't want that either. I want my parameter to also be bounded. So here, instead of just saying that my input, my final instance length is bounded by some function of my initial parameter, I just say that x prime plus k prime should be bounded by a function of k. So it shouldn't explode so it should make the input much smaller so that the input size is bounded by a function of k. And it shouldn't also explode the parameter. The parameter should also remain bounded by a function of k. Now, of course, you can have two different functions for it, or you can just use one. It doesn't really change the definition. Okay. So this is what we mean by a kernelization algorithm. Now, if a problem has a kernel, and if the problem is, let's say, in NP, do you agree that it's solvable in FPT time? Right? So if I take a problem that is already in NP, and I have a kernel for it. So first I run this kernel, and it takes polynomial time. After it takes polynomial time, the size of my input is bounded by a function of k. So I just run a brute force algorithm on this smaller instance, and then that gives me some runtime that is a function of k. So my overall runtime is just going to be the time for kernelization, which was polynomial, plus the time for solving this smaller instance, which was a function of k. So overall, it's FPT. But do we have the other side? So this is what I showed. I showed that if some problem L has a kernel, assuming that L was itself in NP or any other thing. So I just need to have a brute force algorithm for L. But assuming that L is in NP, if L has a kernel, then L is FPT. Now my question is, does this go the other way around? So can I say that if L is in FPT, if my problem has a fixed parameter tractable solution, then it definitely has a kernelization. Now, this would be very weird, but actually the answer is yes. And this is probably the stupidest thing that I have to prove in this class. So when you see the proof, you'll see why. So I want to say that if L has an FPT algorithm, then L has a kernel. Here's the proof. So let's say that A is an algorithm for L, and let's say that the runtime of A is bounded by this expression. So let's say the runtime of A is at most n to the power of some constant times some function of k. Okay? Now, so I don't know anything about what this algorithm does. I just know that its runtime is FPT. Now I just say, take this algorithm. I want to create a kernelization. I say, take this algorithm A and run it for n to the power of c plus 1 steps. Okay? So this is my kernel. I say, run this algorithm A for n to the power of c plus 1 steps. Now, if this algorithm ends in n to the power of c plus 1 steps, then it already gives us an answer, and the kernelization can just give that answer. Okay, so if A terminates, return the answer of A. Weird marker. Okay, but if A doesn't terminate, because you see, I just know that the runtime of A is at most n to the power of c times f of k, but I'm running it for n to the power of c plus 1 steps. So it might be that it doesn't terminate. So if it didn't terminate, just return the original instance. If A does not terminate, and by terminate, I mean terminate within n to the power of c plus 1 steps. Return the original instance, so let's say xk. Now, why is this a valid kernel? Why is this kernelization valid? Well, let's just check all the conditions that we had to have here. First of all, it definitely runs in polynomial time, right? It's taking n to the power of c plus 1 steps, which is polynomial. Now, how about this part? Does it change the answer? It doesn't change the answer. So if A gives us the answer, we're just returning that, which is the correct answer. And if A does not terminate, we're returning the same instance that we had initially. So the answer does not change either. So we have to just show this one. And to show this, to show that the size of the problem always remains bounded by some function of the parameter, we have to only consider this case, the case that the algorithm did not terminate. But what happens in this case? So I know that my algorithm would terminate in these many steps, but it didn't terminate in n to the power of c plus 1 steps. So I should definitely have n to the power of c plus 1 is less than or equal to n to the power of c times f of k. Right? But this basically means that n was less than or equal to f of k. Okay, and if n is less than or equal to f of k, I can just set g to be f of k plus k, right? And then I have this condition as well. So this very, as I said, it's a really unsatisfying proof. It just shows that you can take any FPT algorithm and look at it as kernelization. But this doesn't really have any practical value. In practice, we don't do this. Okay. Now, let's see some real and practical examples of kernelization. And let's see what kind of problems we can solve. So again, our idea is very simple. We want to take our large instance and we want to make it smaller and smaller until we can say that the instance size is bounded by some function of the parent. Okay. So the first problem I want to consider is very similar to a problem we've already seen. And this is the problem of feedback edge set in tournaments. And I'm going to parameterize it by solution size. Now, we've already seen feedback vertex set. So a feedback vertex set was just a set of vertices that when you remove them, you had no cycles remaining in your graph. So feedback edge set is very similar. It's just that you have to remove edges instead of vertices. So the input is a tournament on n vertices. And remember that a tournament was basically a complete graph where all of the edges were oriented somehow, right? And we also have some number k. And the question that we have to answer is whether we can remove k edges from this tournament so that there are no cycles in the tournament anymore. So can we remove k edges to make G acyclic? Okay. So we've already solved feedback vertex set in tournaments. And there the idea was that we were trying to find vertices that had to be in our feedback vertex set or vertices that we were sure were not in the feedback vertex set. And we would just remove those vertices from the graph, right? But the problem here with feedback edge set is that I can't just remove an edge from a tournament. If I remove an edge from a tournament, it's no longer a tournament. Whereas when I remove the vertex from a tournament, I still had a tournament. Okay? So whatever rule I come up with, it can't really remove edges. It has to do something else. It has to preserve the fact that this whole thing is a tournament. So maybe instead of removing an edge, I can just reverse it. So maybe if I have an edge from U to V, and I know that I have to remove this edge because it was maybe in a lot of cycles, maybe instead of removing it, I can just change the orientation from V to U. Okay? So if I can prove this, if I can prove that this doesn't really change my problem, then I can change my question to, can we reverse k edges to make G acyclic? But first of all, why are these things equivalent? Okay. So I have to define some notation so that I can talk about this. So let's say F is a subset of the edges of my graph. So, okay, my graph was VE. So I write rev of F to mean the set of edges that are just reversed. So you take the set of edges in F and reverse each one of them. Okay? And then I write this thing, G star F, to mean the graph G in which all the edges in F are reversed. Okay, so this is the notation I'm using. Whenever I write G star F, I'm taking G, I'm taking every edge in F, and I'm just reversing the orientation of that edge. Okay. So this is the first lemma that I want to prove. I want to first prove that if G star F is acyclic, then F is a feedback edge set in G. So F is a feedback edge set. Okay? Why is this true? So this is actually quite easy. I've taken my graph G and I've reversed some of the edges, right? And after I've done this, there is no cycle in G. If instead of reversing them, I would have removed these edges, I would get a graph that is a subgraph of the graph that I have right now. So that would also not have any cycles in it. So this lemma is super easy. If G star F is acyclic, then F is a feedback edge set. But the opposite doesn't quite hold. For the opposite, I actually need minimality as well. So this is my second lemma. My second lemma is that if F is a minimal feedback edge set, then G star F is acyclic. Okay, but this doesn't matter too much because I'm trying to find a minimal set anyway. I'm trying to answer whether there is a set with less than k edges in it, right? So as long as my lemma works for the minimal sets, I'm happy. So I don't need to say that I want to find just any set of edges and reverse them. I can say I want to find a minimal set, if only I can prove this lemma. So how do you prove this lemma? So let's say that F is a minimal feedback edge set, okay? And to get a contradiction, let's just assume that after reversing the edges in F, we still have a cycle. So let's just take that cycle. And how does that cycle look like? So I have a cycle. And I'm going to put the edges in F with a different color. And by the way, these are all oriented edges, so they have directions. So I might have this edge, for example, and then some other edge, and then maybe again another edge. Okay, so I'm showing the edges that are in the reverse of F in red and all the other edges in black. Okay, so let's say I have a cycle like this. What's the problem with this? Well, F is a minimal feedback edge set, right? So if I remove even one of the edges in F, F will not remain a feedback edge set. What does that mean? That means that each one of the edges in F is in a cycle that only contains that edge and no other edge of F, right? Otherwise, I could just remove that edge from F and F would not be minimal. So this means that this edge, when it was on the other side, when it had the opposite direction, was in some cycle, right? So that cycle can be something like this. Okay. Similarly, this edge, when it was in the opposite direction, was in some cycle. Okay, now you see the problem. I can just ignore the red edges and I can just go through the black edges. So I go through my cycle that I assumed I have in G star F. And whenever I get to an edge that was the reverse of an edge in F, I just take its corresponding cycle instead of taking that edge itself, right? Now, so I found a cycle in G star F, but that cycle only has black edges. So none of the edges in this cycle were reversed. So this cycle also exists in G, in the original graph. And so F was not a feedback edge set. Okay, so this proves the second lemma. So basically now, based on these two lemmas, I can say that I just have to find whether there is a set of at most k edges that I can reverse and then not have any cycles in my graph. Okay, so for this new problem, let's come up with some reduction rules. And I did all of this because I couldn't remove edges. Okay. If I take some edge of my graph, so let's say I have an edge from vertex U to vertex V. When can I be sure that I have to reverse this edge. Okay, so one thing I want you to remember is that we proved last time that if a tournament has a cycle, it definitely has a triangle. So we can just talk about triangles. Okay, so let's take this U and V, and let's take all the triangles that contain this edge. Okay, what do they look like? Well, it's like there is some other vertex, and there is an edge from V to that vertex, and from that vertex to U. Let's just count how many vertices like this we can have. So let's say I have a lot of vertices like this. Now, I have to get rid of all of these triangles. So if I don't reverse this edge, I have to reverse at least one edge in each one of these triangles. So if I have more than k triangles, I wouldn't be able to do that. So my first reduction rule is if I find an edge UV that is in more than k triangles, I have to put that edge into my solution. I have to definitely reverse that edge. So this is reduction rule 1. If some edge UV is in k plus 1 or more triangles, then my instance, gk, would just become G, in which I've reversed U and V. And now I have a budget of k minus 1. Okay. So my next rule is about a vertex that doesn't appear in any triangle. So let's say I have a vertex V, and this vertex does not appear in any triangle. I want to say that I can remove this vertex. And again, remember that removing vertices is fine because it keeps it a tournament. Okay, so let's have a picture here. Let's say I have some vertex V, and there are some vertices that have edges to V. Let's call them, I don't know, X. So all of these vertices have edges to V. And there are some other vertices that V has an edge to them. Let's call those Y. Right? And this is a partition of all the vertices because it's a tournament. So any vertex that I take either has an edge to V or V has an edge to that vertex. Now, what does it mean when we say we don't have a triangle? It means there is no edge that goes from Y back to X. Right? Otherwise, V would be in a triangle. Now, I claim that if this is the situation that we have, if there is no edge from Y back to X, then I can just remove V. Now, why is that? Let's suppose that I have a solution, and let's suppose that that solution is really reversing some of the edges that had V as one of their endpoints. Would that be useful at all? So you see, if I have a cycle that is entirely in Y, reversing this edge would not help. If I have a cycle that is entirely in X, reversing this edge would not help. And I don't have a cycle that has both X and Y in it. Right? So in any case, reversing these edges that are going out of V would not help. They don't remove any cycles for me. So yeah, I can always just remove V. So this is my second reduction rule. If some vertex V appears in no triangle, and by triangle, I mean a directed cycle with 3 vertices. Okay? Then just take your instance GK and remove the vertex V, and the budget remains the same. We're not in reversing any edges. Okay. So as usual, we just apply these rules as many times as we can, right? So we keep applying these until we get to a graph on which we cannot apply any of these rules. Now we want to say how big can this graph be? Okay. And again, as usual, I want to say that if this graph is too big, I can just immediately say the answer is no and not look into it anymore. But if the answer is yes, then this graph is going to be small. That's what I want to show. So let's say I've applied these rules as many times as I could. And now let's just assume that the answer is yes. So if the answer is yes, how many vertices can I have remaining in my graph? Okay. So what do I know? If the answer is yes, I know that I can just reverse k edges, right, and not have a cycle. So let's just call those k edges f again. So let f be the set of k edges that I can reverse to remove all the cycles from my current graph, the remaining graph. Okay. Now just take some edge in f. So let's say this is an edge, edge E, and let's say that this edge E is in f. What do I know about this edge? Well, according to rule 1, I know that it is in at most k triangles. Because if it were in more than k triangles, I would just apply rule 1 already. Okay, so let's just consider all the triangles that contain this edge. So they look something like this. Okay. But on the other hand, I know that every vertex appears in at least one triangle. Otherwise, I would have removed it. Right? And also, this set E, it's a feedback edge set. So this set F, it's a feedback edge set. So every triangle has to have at least one of its edges in F. Right? So now I have k edges in F. How many triangles can I have? I can have k squared triangles, right? Because each of these edges is in at most k triangles, and even assuming that all of those triangles are completely separate, I get k squared triangles. So if I have k squared triangles and every vertex appears in at least one triangle, how many vertices can I have? I can have at most 3k squared vertices. So this shows that after I apply these rules as many times as I could, if the number of vertices in my graph is more than 3k squared, I can just immediately say the answer is no. And if the number is less than 3k squared, I have a kernel, right? And now I have a graph that is really small and its size is bounded by some function of k. So in this graph, I can just do brute force. So in any case, I got an FET algorithm. But actually, we can find a kind of a better bound here. So instead of 3k squared, I can do even better. Here's the thing. Consider this edge E. So what is the number of vertices that appear in triangles that contain E? Well, I have at most k vertices here, and I have 2 vertices here. So it's k plus 2. But if I just create the same picture for every edge, I will get k copies of this. So the total number of edges is at most k times k plus 2, which is like a constant factor better than 3k squared. Okay. This is one example of how kernelization works. Now, let me go to a different example. My second example is something called edge click cover. And this is again parameterized by the solution size. So in this problem, I again have a graph. So let's say I have a kite-like graph. And maybe another copy of it. Let's add this edge. Let's add one edge here. Okay. Let's say I have this graph. And I want to cover all of the edges of this graph with a bunch of clicks. Okay? And the question is whether I can cover it with k clicks, and k is the parameter. So I give you a graph, I give you some number k, and I ask you, can you cover all the edges of this graph with k clicks? And of course, the clicks cannot have any extra edges in them. So I want some clicks, let's call them C1, C2 to CK, such that when I just take the union of all the edges in these clicks, I get my original graph G. Okay. So for example, in this case, I can cover this with 4 clicks, right? So this is 1 click, this is 2, this one is 3, and this is 4. Right? And as you see, the clicks can have intersection, but they shouldn't create any edges that are not in the original graph. So this problem is called edge click cover. So can we cover the graph with k clicks? And again, k is the parameter. So I want to find a kernelization for this one. Let's just look at reduction rules that we can come up with. So first of all, what happens if I have a vertex of degree 0? A vertex of degree 0 has no edges. So I don't need any clicks for it. It doesn't really contribute anything to the problem. I can just remove it. So this is my first reduction rule. If the degree of V is 0, then just take your instance gk and turn it in g minus v and k. Okay, what if I have a vertex of degree 1? So what if I have a vertex that looks like this? Actually, let me just write it in the rule. So this is reduction rule 2. Let's say I have a vertex u that is connected to a vertex v, and the degree of u is 1. So this is the only neighbor of u. Well, I know that I have to cover this edge, right? And the only way that I can cover this edge is to take these 2 vertices as one of my clicks, because this vertex has only degree 1. So then I have to just take my instance gk, and I would turn it to g minus this edge from u to v. Okay, or let me just write it g minus u, because I can just remove vertex u as well. And k minus 1, because I've now used one of my clicks. Okay, what else can I do? Is there a case where I can say that 2 vertices are definitely going to appear in the same set of clicks? So, for example, here, let's look at these 2 vertices, right? So what are, let's just give them some number. Let's say this is 1, 2, 3, 4. I don't need numbers for the rest. So let's look at vertices 1 and 2. What are the neighbors of 1? It's 2, 3, and 4. So if I get the closed neighborhood of 1, which means the vertex itself and all of its neighbors, the closed neighborhood of 1 is just 1, 2, 3, 4. The closed neighborhood of 2 is also 1, 2, 3, 4. So it makes sense to always put 1 and 2 into the same clicks, right? Because whenever I have a click that contains vertex 1, Well, of course, all the neighbors of 1 are also neighbors of 2. So I can just add 2 to that click. And I potentially cover some new edges for free. Right? And the same thing in the opposite way as well. So this is my third reduction rule. My third reduction rule is that if 2 vertices have the same neighborhood, just remove one of them. Because you can find a solution for the rest. And after you found a solution for the rest, if you had removed, for example, vertex 2, you just look into your solution and see all the clicks that contain vertex 1. And you just put vertex 2 into all of those clicks. So if the closed neighborhood of a vertex U is the same as the closed neighborhood of a vertex V, then I just get my graph GK and I turn it into G minus, I don't know, either remove U or V. So I'll remove V and my budget remains the same. Okay, these are our reduction rules. So again, as usual, we just apply these reduction rules as many times as possible. So let's say I applied them as many times as I could, and now I finally have a graph over which none of these rules are applicable. Okay? What can I say about the size of this graph? Again, I want to say that if this graph is too large, then the answer is immediately no. Okay? So just as before, I assume that I have a solution. And then assuming that I have a solution, I find the bound on the size of the graph so that I can say that if my graph is larger than that, the answer is definitely no. Okay, so let's say I have a solution C1, C2 to CK. Okay? Now here's what I do. I just look at every one of my vertices and I check which one of these clicks contains that vertex. So let's say I take vertex 1, and for vertex 1, I just write like a binary sequence of zeros and ones. If vertex 1 is in my first click, I write a 1 here. Otherwise, I write a 0. If vertex 1 is not in the second click, I write a 0. If it is in the case click, I write a 1, and so on. So I have n vertices here. And to each of these vertices, I'm assigning a binary sequence of length k, which basically tells me which one of the clicks contains that vertex. Now, what happens if 2 vertices have the same sequence? So let's say vertex 1 and vertex n appeared in exactly the same clicks. So if they appeared in exactly the same clicks, that means these 2 vertices have the same neighbors, the same closed neighborhood, right? Because these clicks are covering all the neighbors of vertex 1, and they're also all the edges going out of vertex 1, and they're also covering all the edges going out of vertex n. So if the set of clicks that contain vertex 1 is the same as the set of clicks that contain vertex n, then the closed neighborhood of 1 and closed neighborhood of n were the same. So I had to remove one of them. So that would be a contradiction because I assumed that I've applied these rules as many times as I could. So this basically shows that after I apply all of these rules, the number of my vertices, n, has to be at most 2 to the power of k, because I can have at most 2 to the power of k different sequences here, right? So now what is my algorithm overall? Well, I just apply these rules as many times as I can. And after I can no longer apply these rules, I just check. And if I have more than 2 to the power of k vertices, I just immediately say the answer is no. If I had less than 2 to the power of k vertices, or at most 2 to the power of k vertices, that's the kernel. I have a small graph, and now I can do brute force on it. And whatever I do in it, it's going to take a time that is a function of only k. Okay. Nice. So I'm now going to switch to a different technique, which has very similar ideas in it. And this technique is called iterative compression. So let's look into our favorite problem, which is vertex cover. We've already seen two different solutions for how we can solve vertex cover parameterized by solution size. We're going to see more. So this is my problem. So vertex cover parameterized by solution size. Again, the input is just a graph G and some number K. And the question is, can you remove K vertices so that there are no edges remaining in G? So we want to find K vertices that cover all of the edges, or equivalently, we want to remove K vertices so that no edges remain. So can we remove K vertices to make G edgeless? Okay. So now, what is the main idea in iterative compression? What do I mean when I say compression? So the technique is, suppose I give you a solution, but the solution is a little bit larger than what you want. So maybe you want to find K vertices, but I give you a solution that has K plus 1 vertices in it. Can you somehow use that solution to compress it down and get a solution with K vertices? So that would be the compression problem. I'm going to define it here. So let's call it vertex cover compression. And again, this is parameterized by solution size. Now, in this one, the input is everything that we had before. So I have G, I have K, but I also get a vertex cover of size K plus 1. Okay? And a vertex cover, let's call it S, of size K plus 1. And the question I have to answer is the same. Is there a vertex cover of size K? Can I find a vertex cover that is one vertex smaller than the thing that I'm given? So my question is just, is there, let's call it a K vertex cover, a vertex cover with K vertices. Now, for a second, just assume that I give you an algorithm for this one. Let's say you have an algorithm for this one. Can you use that algorithm to solve the original problem? Actually, the answer is yes, and this is where the name iterative compression comes from. So I just take my graph G, and I add its vertices one by one. So I just create a sequence of subgraphs of G. Okay, so I start with the empty graph. So I can show it like this, the empty graph. And then I add my first vertex. And then I get a graph G that has only vertex number 1. Then I add my second vertex, G, that has vertices 1 and 2 only. And I continue this. I just add my vertices one by one until I get my whole graph G that has all the vertices from 1 to n. Okay? Now I say I want to find a solution for every one of these subgraphs. Okay? So for the first one, the solution is easy. It's an empty graph. So just the empty set is a solution. So I'm going to call that S0, solution 0, which is just the empty set. Now, how about this one? A graph that has just one vertex. Again, the empty set is a solution, right? And so I can say S1 is also empty. How about this one? I have 2 vertices. Well, I can just take the solution that I had before, and I've added one new vertex to my graph. I can just add that vertex into my solution as well, right? And generally, I can do this as long as I have less than k vertices, right? So as I'm going here, up until the point where I have my first k vertices, I can just say add all of them to the solution, because I just want a vertex cover of size at most k for each one of these graphs. So here I say my solution is just 1 and 2 maybe, and here I just say my solution is 1, 2, k. Now what happens from this point onwards? Every time that I add a new vertex, I can just add it also to the solution. But my solution used to have size k before, so now it might have size k plus 1. But I can always just ask for this compression problem. And let's just assume that it doesn't only answer this question, it also gives me the result as well, right? So instead of saying, is there a k vertex cover, it also returns it if there is. Okay? So when I add my k plus first vertex, I get g from vertex 1 to k plus 1. And I just add it to my solution. So my solution now looks like this. It's 1 to k plus 1, but it has size k plus 1. So I just call this compression. So I just do the compression. I compress it. And there are two cases. Either the compression gives me a solution of size k, in which case I'm happy and I just continue this process. Or it says that there is no solution of size k, which means that even this subgraph here didn't have a vertex cover of size k. So the original graph can also not have a vertex cover of size k. Okay. So overall, if I have a solution for compression, I get a solution for the original problem that just calls this compression algorithm at most n times, n minus k times, but k is much smaller than n, we assume, so at most n times. So in other words, if I have a solution here that takes a time, let's say fpt time, n to the power of c times f of k, then that would directly give me a solution on this side that takes n to the power of c plus 1 times f of k time. Right? Because I'm just doing this n steps, and in each step I might call a compression. Okay. So now I know that I have basically reduced this problem to this problem. So I can only focus on this one, and I have to only solve this one. How do I solve this one? So I'm given some graph, and I'm also given a vertex cover of this graph, but this vertex cover is a little bit larger than what I wanted it to be. It's just, it has one more vertex than what I liked. Can I find another vertex cover that has one fewer vertex? Okay. So here's the thing. Let's say that I just put my vertex cover here. So this is my vertex cover of size k plus 1. Let's call it, I don't know, let's call it A. So this is A, and the size of A is just k plus 1. And let's say this is the rest of my graph. Okay. What do I know? Well, A is a vertex cover. So there can be no edges here, because this edge would not be covered by A. So in other words, the rest of the graph is just an independent set. And I have my vertex cover here, and any edge that I consider is either from the rest of the vertices to the vertex cover, or potentially in the vertex cover itself. These are all the places where I can have edges. Okay. Now I want the vertex cover that is a little bit smaller? Well, I can just do some sort of branching. It's not exactly branching, but like, yeah, I can do a casework over how many of these vertices in A and which vertices in A are going to be in my smaller solution. So let's say that the smaller solution that I want to find is B. Okay, so I just want to see what is the intersection of B and A. And I don't know it, so I try every subset of A. So I try every subset of A, and I ask, is there a vertex cover B that has size K, and its intersection with A is that subset? Okay, so let me write it here. For every, let's call it C, for every subset C of A, I ask, is there some vertex cover B such that it has K vertices and B intersection with A is C? Okay. So this 4 has to try 2 to the power of K plus 1 different subsets of A, because A has size K plus 1, right? So if I can answer this question with a fixed A, then I can also do the whole thing, and I just get a factor of 2 to the power of K in my runtime. Okay, but what happens if I take some subset C here? So let's say this is C. And if I say I want my solution B to intersect A only at C. Okay, so this means that I know the vertices in C are going to be in my solution. And remember, when we were working with vertex cover before, whenever we knew that a vertex is in the solution, we could just remove it from the graph, right? This vertex is going to be in my solution, I just remove it from the graph, right? So I remove all these vertices from my graph, and now I have some other vertices left here. And now I'm just looking for a solution that only takes vertices from up here and nothing from down here, right? So this problem, I can give it another name. This is called disjoint vertex set. So let's say disjoint vertex set. And it's also going to be parameterized by solution size, of course. But I'll just write the parameters in here. So what is my input? My input is, again, my graph G. Now, I have some remaining part here. So, and it's going to be a vertex cover because I've already removed these vertices and all of the edges from them. So I have my graph G, I have a vertex cover of G, and let's say that these remaining parts, they don't have K vertices anymore. So let's say, I don't know, S vertices. So vertex cover of G with S vertices. And the question that I have to answer is there another vertex cover of G that is completely disjoint from this one and has some other number of vertices? So let's say I have a vertex cover of G. Let's give this a name. So this remaining part, it's like A minus C. So let's just call it D. So I have a vertex cover D of G. And D has, okay, let's call it D vertices so that it's easier to remember. And the question is there another vertex cover of G? Let's say this one with F vertices. And let's call the vertex cover itself F, such that F intersection with D is empty. Okay. Again, how did we get here? We got here from the compression. So we said we have a vertex cover of size k plus 1, which is A. We want to find a vertex cover of size k. We just try every possibility for their intersection. So I say for every C that is a subset of A, suppose that I want to find the vertex cover of size k that intersects A at C. So if it intersects A at C, all the vertices in C have to be in my vertex cover, so I can remove these vertices from the graph and I can remove all of the edges from them. So I get another graph and I have a vertex cover in that graph, which are the remaining vertices here. And my question is, can you give me another vertex cover on the other side of the graph such that there is no intersection between these two vertex covers? So this is the disjoint vertex cover problem. We see. Okay. Now, again, if I can solve this one in FPT time, then I can just solve it 2 to the power of k times, and then I can answer this one. So how do you solve this one? So if I give you a graph and a vertex cover, and I ask you, can you give me some other vertex cover that is disjoint? And what are our parameters? Now we actually have 2 parameters. We have this one, which is the number of vertices in the vertex cover that is given in the input. And we also have this one, which is the number of vertices in the vertex cover that we want to find. And we just assume that both of them are small, both of them are parameters. Okay, or equivalently, I can say my parameter is D plus F. Okay. Now, this one is actually quite easy. So let's just draw a picture like that again. So I have a vertex cover, and I have the rest of my graph. Okay? So this side is a vertex cover. So it means that any edge that I take has at least one of its endpoints down here. So there are no edges up here. So up here, I have an independent set. So this is an independent set. Okay? But what happens if I have an edge that is entirely down here? What happens if I have an edge like this? You see, I'm asking for a disjoint vertex cover. I'm asking for a vertex cover that only has vertices from up here. So if I have an edge down here, the answer is immediately no. I know that I don't have any such vertex cover. Otherwise, this one is also an independent set because there is no edge down here. So the only case that I have to solve is if both of them are independent sets, and basically I have a bipartite graph, right? All of the edges go from the part up there to the part down here. And I might have some. Now, again, what do I know? I know that this part, the lower part, is a vertex cover. Okay? But I want to find the vertex cover. I want to find a way of covering all of these vertices without taking any vertices that are down here. So I have to take all the vertices up here that have an edge going out of them. Right? There's no other way. So I can simply, to answer this question, I mean, I don't even need the parameters. It's completely polynomial time. I can just look and see if in my vertex cover I have an edge. If I had an edge down here, the answer is immediately no. If not, I have a bipartite graph, and instead of taking vertices from this side, I can take vertices from that side, except for isolated vertices, of course. And then I can just count them and see how many I have. And if I have more than F, I say the answer is no. If I have less than F, I return. So this one is super easy to solve. So how much time does it take for me to solve this one? It's basically the number of vertices plus the number of edges, right? So I'm solving this one in, let's call it n plus m, assuming that I have n vertices and m edges. So now how much time do I need for this one? Well, I'm just trying 2 to the power of k plus 1 different values for C. And for each of them, I'm making a call to disjoint vertex cover. So this one is solved in time 2 to the power of k plus 1, but I just write 2 to the power of k because I don't care about constants, times n plus m. Okay. But we said that if we can solve this one in n to the power of c times f of k, I just get an extra factor of n here. So now this one is solved in O 2 to the power of k times n squared plus nm. Okay? Now, yeah, this is not necessarily better than the things that we had before, but it just shows that you can do this idea of compressing the problem over and over again. So I'm going to show you another algorithm where actually this compression really gives us a much better bound than what we had using branching. So for vertex cover, using branching, we already had an algorithm that took 2 to the power of k, and here it was linear instead of quadratic time. So this is already worse than branching. But I want you to see the general idea here. The general idea is that I have, let's say, a graph, and I want to remove some vertices, or maybe in some problems, I want to remove some edges so that the graph has some property at the end. In this case, I want the graph to have no edges at the end. Now, the way I do that is that I consider a compression problem. I just consider what happens if I have a solution that is that has one vertex or one edge more than what I require. And I try to solve that one and then use it to solve the original problem. Now, to solve the compression problem, I say I already have a solution. I want to find another solution, which is smaller. What is the intersection of these two solutions? I just try every possible intersection, right? And that reduces the problem to the disjoint variant of the same problem, which says that I have some solution and I want to find another solution, but I want it to be completely disjoint. Okay. So we don't have much time, so I don't think I would be able to finish the next example, but I started and then we can get back to it next session. Okay. Our next example is our second favorite problem, which is feedback vertex set. And we've seen this many times before. So I just want to have feedback vertex set, again, parameterized by solution size. So remember what this was? Feedback vertex set was just that you have some graph and you want to remove some of the vertices so that there are no edges remaining in the graph. And I'm assuming that I have an undirected graph here. And let's say that I'm given some number k, and I want to remove at most k vertices. So that's the part where I say it's parameterized by solution size. Now, I want to solve this using the same idea, using the idea of iterative compression. Okay? So I create my subgraphs. I just start with the empty graph. And I say in the empty graph, nothing is a solution. Right? Then I add my first vertex. And I also add it to my solution. And I do the same thing until my case vertex. I say my solution here is just 1 to k. Now, when I add the k plus first vertex, I also add it to my solution. And now I have a solution with k plus 1 vertices. But that might be too large. So I just ask, can I compress this down to get k vertices? So I do a compression here. and there are two cases. If it's successful, I get a solution with at most k vertices. And if it's not successful, I just return no. Because there is no way to remove k vertices even in this subgraph so that I don't have a cycle, right? And from this point onwards, I just continue with this. I always have a solution of size k. I'm adding a new vertex. I add that vertex to my solution. I have a solution of size k plus 1. And then I try to compress it. If I can't compress it, the answer is no. If I can compress it, I have an answer and I can continue. Okay, so this is fine. So now I have to solve feedback vertex set compression. Okay. And so I'm given a solution of size k plus 1. I want to find a solution of size k. But again, I do exactly the same thing that I was doing before. I say consider the solution that I'm given. So let's say this is my solution A that has size k plus 1. And let's say this is the rest of my graph. And this is a feedback vertex set. So any cycle has to come through this lower part here. Okay? I just say if I'm supposed to have another solution that is smaller, if I'm supposed to have like a solution B, let's say this is B, it's going to intersect A at some point, or maybe the intersection is even empty, but in any case, I'm going to call the intersection C. And I'm going to consider all the possible intersections. Okay? Now, if I know that the intersection is C, what do I know? I know that the vertices in C have to be removed. Because in a feedback vertex set, I'm removing a bunch of vertices to have no cycles. So I just remove the vertices in C, and the rest of, in the remaining graph, the rest of A is going to be a feedback vertex set, right? So I now say that I need to find the rest of B. I need to find this part, and it has to be disjoint from the rest of A, this part. So in other words, I'm changing feedback vertex set compression to feedback vertex set, disjoint feedback vertex set. So now my problem is that I'm given some feedback vertex set and it's a small one, and I want to find another feedback vertex set of a different size, but both sizes are given to me as parameters. Right? And I want them to be disjoint. So I have this feedback vertex set, let's call it F. And let's say that F, okay, sorry, no, let's call it D. And let's say that it has D vertices in it. And in the rest of my graph, I want to find another feedback vertex set F. Okay? Now, what do I know about the rest of my graph? I know that D was a feedback vertex set. So the rest of my graph doesn't have any cycles in it, right? So this part up here, it's a forest. So let's just consider it a forest. Now, I want a solution that only takes vertices from this forest. And I can also have edges from this forest up here to D down here. But before that, before trying to do anything else, let's just look at our graph restricted to D. So let's just look at the induced subgraph by D. So I'm just ignoring the rest of the graph and only looking at what's happening in this part. Now, can I have a cycle in here? Can I have, for example, a triangle or any kind of cycle? No, because if I have a cycle here, my answer is immediately no. Because I have to remove a bunch of vertices from up here so that there are no cycles. But if there's a cycle that is entirely down here, the answer is definitely no. What does this mean? It means that this one also has to be a forest. Okay. So let's say I have a forest. Now, here's what I claim. I claim that I can take this forest and I can take any of the trees, any of the connected components of this forest, and I can merge all of the vertices in that tree so that I just have one vertex in place of that tree. And this would not change any of the cycles that I have. Okay? Why is that? Because every cycle has to go through both parts, right? So if I have a cycle that, for example, uses this tree, that cycle at some point comes to one of the vertices in this tree and then goes some path inside this tree and then goes out from somewhere else. But if I just merge all the vertices in this tree into a single vertex, I would still have the same cycle. Okay? So in other words, without loss of generality, now I can assume that this set D is an independent set, because it's just a bunch of vertices, and I've put one vertex for each one of the trees that I had before. So I just do this pre-processing, and now in my set D, I just have a bunch of isolated vertices. Of course, they can be connected to vertices up here, right? So I can have edges like this. Okay. And also I can have multi-edges now. So I have to be careful about that, right? Because I could have, maybe it was the case that this vertex here had edges, had two edges to a tree down here. So now that tree is just one vertex and this vertex has two edges to that. Okay. Now, in the next step, I'm going to say, take some leaf up here. Okay, so let's say I take this particular leaf, and a leaf is just a vertex of degree 1, and every forest has a leaf, so I can always find a leaf. Now, what happens with this leaf? If this leaf has no edges to the parts down here, what can I say? If it has no edges down here and it only has one edge up there, it's never optimal to take this one into my vertex cover. It's always optimal to take its neighbor. And in this case, the neighbor also has degree 1. So let me just make sure that the neighbor has a higher degree. Okay, so that's my first reduction rule. If I get a leaf up here and it has degree 0, if it doesn't have any edge to D, then I don't take that, and I can just take its neighbor into my feedback, into my, okay, now, let me see, what can I do? Yeah, sorry. So if I have a leaf here, it doesn't have an edge down here, so it's not a member of any cycles. It doesn't appear in any cycles. For a second, I was thinking about vertex cover. So if it's not a member of any cycles, I can just remove this leaf, right? It doesn't appear in any of my cycles, I don't need it. So this is my reduction rule 1. If I have a leaf, so let's say L is a leaf in, okay, this one was D, so let's call this one U, is a leaf in U and has no edge to D. Then I just remove it. So I just get my instance GK and I remove this vertex L from it and I don't change my budget. Okay, what if it has exactly one edge to D? What if I take, for example, this leaf and I see that it has just one edge to D? What can I say about this case? Now, if the leaf has exactly one edge here, it means that it has exactly one neighbor in U because it was a leaf, and it has exactly one neighbor in D, right? So it has degree 2. But in that case, any cycle that goes through this vertex has to also go through both of its neighbors. So specifically, any cycle that goes through this vertex has to also go through this one. So it's not optimal for me to take this vertex into my feedback vertex set. It's always better to take this neighbor. So I can just get rid of this vertex, and I can just connect its two neighbors together, and the cycles don't change. And this was also a sound reduction. Okay? So this is my second reduction rule. If L is a leaf in U, and let's say its neighbors were, I don't know, let's call this one V and this one W, with neighbors V in U and W in D, then what I do is that I just take my graph and I remove the leaf L from it, and I add an edge from U to W. So here I'm in an edge. So it's not that I'm adding two vertices, I'm adding an edge. Sorry, from V to W. Yes. And my parameter remains the same. Okay. Now, I apply these rules as many times as I can, of course. But the remaining case, for which we don't have time right now, is if I have a leaf and it has a degree of more than 2. Okay? Sorry, it has a degree of 2 or more. So let's say I have this leaf here, and maybe it's connected to 2 vertices in T. So what can I do then? Well, I just give you the answer, but I'll do the analysis next time. I just branch on these leaves. I just say there are 2 cases. Either this leaf is in my feedback vertex set or it's not. And I solve the 2 cases by branching. Now, why does this branching work? Because if this leaf is in my feedback vertex set, then when I'm branching, the size of my feedback vertex set is going to be smaller, right? If this leaf is not in my feedback vertex set, I can just move this leaf from up here to down here, right? And that would, and I again said that when I move something here, whenever I have a tree down here, I merge it into one vertex. So that would reduce the number of vertices down here. So when I'm doing that branching, every time, either my parameter, my budget for my feedback vertex set goes down, or the size of the solution down here goes down. And so my branching actually ends. Okay, I'll do the details of this next session and see you on Thursday.